We have now we're going to move back to also alpha activity and looking at scenes and scene complexity. And that's something that's also interesting. And we're going to look at data now in kids and adolescents. And so Chin Yin is going to take us through that. So Chin, the floor is yours.
Thank you for having me. I'm Qing from Wayne State University. I'm a graduate student in Department of Psychology. And today I'm going to talk about the relationship between the maturation of the occipital cortex and memory development. So it is well known that the ventral temporal cortex has fusiform face area and parahippocampal place area. And previous studies have found that the size of functionally defined parahippocampal place area and fusiform face area increase with age. And this age-related increase in the activation area to places or faces is associated with development of category-specific recognition memory, suggesting the link between the development of high-level visual cortex and category-specific recognition memory. And the processing of low-level visual information, such as color perception, also shows developmental gains through childhood and adolescence, so probably due to the developmental changes in the occipital cortex. And it has been established that the age-related gains in memory performance are associated with development of prefrontal cortex and medial temporal lobe. However, memory for visual stimuli depends on the input from the occipital cortex. So it is unknown if the functional maturation of the occipital cortex supports the development of memory for complex visual stimuli such as scenes. So in our study, we used intracranial EEG recording in which subdural electrodes are implanted in epilepsy patients for seizure management. And thank you, Lisa, for such great introduction for the intracranial EEG recording. And it has a high temporal resolution and superior signal to noise ratio. So here is an example of electrode coverage of one patient. And we analyzed the data from occipital cortex from 24 participants aged 26 to 20 years old who had occipital cortex electrode coverage. And here we showed the electrode coverage on the group level, and the electrodes were color-coded by participant age. And in order to examine memory-related signal, we used a scene subsequent memory paradigm. So I'm going to just go over this paradigm pretty quick. Participants studied pictures of scenes in preparation for a recognition test. And during the test, they had to respond if they saw this picture before or not. And based on their recognition response, the studied pictures were labeled as subsequently recognized or subsequent hit or subsequent miss pictures. So by analyzing data from the encoding block, we were able to look at the occipital signal that is related to memory formation. And in order to approximate different levels of visual processing during memory encoding, we classified things as high or low complexity things defined by the unique by the number of unique object categories depicted in the scene. So as you can see here, high complexity things has more than 4 object categories, and the low complexity thing has less than 4 object categories. And first, let's look at memory performance, which is measured here as recognition accuracy. And we plot age on x-axis and recognition accuracy on y-axis. Blue color represents the complexity thing, recognition accuracy, and orange represents low complexity thing. And we found age by complexity interaction, which shows age-related increase in recognition accuracy for high complexity things, but not for low complexity things. And our behavioral results are consistent with the previous study in normal participants. And the memory performance results confirm that there is visual complexity effects on memory. And next, we examined if and how the occipital cortex is associated with this age-related increase in memory for complex things. So in our study, we examined alpha oscillations from the occipital cortex because they are the most prominent features in the visual regions. We examined two different aspects of alpha oscillations, the broadband alpha power and instantaneous alpha frequency. So it has been shown that the decreases in alpha power are associated with increases in neuronal activity, hemodynamic responses, and alpha power decreases indicate richness of information encoded and can predict memory outcome. And alpha frequency indicates the speed of the oscillation, and it is consistent with the notion of rhythmic perception and has been shown to relate to the temporal resolution of visual perception.
Just to stop you for a minute, Chin, there's a little bit of a problem with the sound that you've got. It's a little bit muffled, at least as I'm hearing it. So I don't know if you can turn up your volume a little bit. Sorry to interrupt you.
Oh, okay. So so it's now better now?
I can hear it a little bit more clearly because it was just breaking up a little bit. Okay, thank you.
Okay. Okay, so now let's first look at subsequent memory effects in alpha power. Here I first show the scene viewing induced power change. So the 3 seconds of scene presentation is on x-axis and frequency is on y-axis. So the solid vertical line indicates the scene onset and the dashed vertical line indicates mean response time. So power change after scene onset is color-coded. And here we can see scene viewing induced power decreases in alpha range for high complexity hit, high complexity miss, low complexity hit, and low complexity miss. So next, we looked at if there are differences in power decreases between subsequent hit and miss pictures. So we analyzed the subsequent memory effects, which are the differences in power between hit and miss. And we found significant negative subsequent memory effects in high complexity scenes across the whole scene perception period. Here, the enclosed areas indicate the data points of significant subsequent memory effects. And few subsequent memory effects were observed in low complexity scenes. So these results demonstrate that scene viewing induced power decreases in the alpha range, and decreased alpha power benefits memory formation for complex visual scenes. And next, we looked at the complexity by age interaction effects in the alpha power because we wanted to know if there is difference in age-related changes in alpha power between high and low complexity scenes giving the observed behavioral results. So here we show the F statistic of complexity by age interaction for subsequent hit scenes. And as you can see, we observed significant complexity by age interaction in the middle of scene perception. So to unpack this interaction effect, we averaged the power within this time frequency windows for each participant and for high and low complexity scenes separately. We plotted the averaged power by participant's age. As you can see here, the complexity by age interactions were driven largely by an age-related decrease in power during the encoding of high complexity scenes, but not low complexity scenes. And next, we looked at if this age-related decrease in alpha power for high complexity scenes predicts memory performance. So we found age by accuracy interaction for high complexity things in which lower alpha power predicted a greater high complexity recognition accuracy among adolescents. And this relationship was largely absent among children. And low complexity power was not related to recognition accuracy or the interaction of age and accuracy. So our results demonstrate age-related decrease in alpha power during the encoding of high complexity things, and also alpha power decrease is related to age-related gains in the recognition of high complexity things. And next, let's look at alpha frequency. Here, I first show the dynamics of instantaneous alpha frequency for high and low complexity things over the 3-second thing perception for subsequent hit and for subsequent miss things. And the 3-second thing perception, again, is also on x-axis, and the frequency of alpha is on y-axis. Again, we wanted to know if there is difference in age-related changes in alpha frequency between high and low complexity things. So we show the alpha statistic of complexity by age interaction on alpha frequency for subsequent hit things. And as you can see, we observed significant complexity by age interaction in the middle of scene perception, and this time window overlaps with the time window of the same effects in alpha power. To unpack this interaction effect, we again averaged instantaneous alpha frequency within this time window for each participant, and for high and low complexity things separately, and plotted the averaged frequency by participant's age. So as you can see, the complexity by age interaction were driven largely by an age-related increase in alpha frequency during the encoding of high complexity things, but not low complexity things. And we didn't observe any accuracy effects on alpha frequency. So the results here show age-related increase in alpha frequency during the encoding of high complexity things. And taken together, we found age-related increase in memory performance for high complexity things, and we also found that age was associated with decreased alpha power and increased instantaneous alpha frequency during the encoding of subsequently recognized high complexity things. Third, we found that the decreased alpha power predicted improved recognition of high complexity things in adolescents, providing evidence linking the functional maturation of the occipital cortex to the development of memory for complex things. And these results were published on Neuropsychology. And I'd like to thank everyone who helped in this project, and I'm happy to answer questions.
Okay, thank you very much, Jin. Can you go back to your previous slide so everyone can see that paper? Aha, because I searched for that and I didn't find it. So thank you for sharing it for everybody. We have a question from Devin Kassenheiser. I hope I pronounced that name correctly. And he says, if I can ask you to speculate, do you think the power differences you observe for memory, age and accuracy reflect efficiency of memory usage or something else?
So here we so if we think memory usage, then we would link to how previous knowledge can affect how we encode the information, if I understand the question correctly. Yes, I think so. The power we decrease in occipital cortex is only in the occipital cortex, but it may be modulated by the prefrontal cortex or the medial temporal lobe, and by the top-down interactions. So if the top-down interactions may help reduce the alpha power. So I think it's possible that it's related to the memory usage. I hope I addressed this question.
He says that makes sense. Thank you for that. And so I don't see any other questions. So I've got another one. I've got a quick one. These results are fascinating, these low frequency results. And I wondered about cross-frequency coupling of these rhythms with the higher frequencies. Have you had a chance to look at what happens at some of the higher frequencies and how their power distribution relates to what happens to activity in the alpha range as it increases and decreases?
Yeah, that's a great question, and we haven't looked at that, but we are planning to look at that. So in one of our results, we found this increased frequency, and maybe this increased frequency will give more time window for like high gamma to couple with the alpha frequency. So yeah, we are following up on that analysis.
Great, thank you so much. Well, this was a great three.